Thank you for joining us for the very latest Prism Sound Wednesday webinar. Today's topic for discussion will be test techniques for tablets and other audio playback devices. We will spend a little bit of time talking about exactly what we mean by this title, and we will then spend some time looking at some live measurement demonstrations illustrating the theory and practice of how to go about measuring this particular category of audio device. A brief introduction to me. My name is Simon Woolard and I am an applications engineer here at Prism Sound headquarters in the UK, and it's my responsibility to ensure that people who use Prism Sound's test and measurement equipment get the most out of the solutions, and to help to educate our clients and prospective clients about solving their audio test and measurement needs. So I will be taking you through today's formal presentation, and I'm also joined by my colleague Graham Boswell, who will be dealing with any support issues in the NetViewer chat as we go through the presentation. If you have any questions, please do post them. We will come back to questions related to the content at the end of the session. So before we get into today's formal agenda, I'd just like to involve you, and I want to ask you a question that relates to the topic, the headline for today's presentation. So those of you that are using a PC will see a survey question appear on your screen. And in particular, I would like to ask you whether you appreciate what it is that's particularly challenging about testing playback-only audio devices. And I've given you several options to choose from. I would like you to choose what you think is the correct answer to this question. And there is also then a second question asking you about your specific area of interest in audio test and measurement, the main reason why you have attended today. This survey will help give us a better understanding of who we're talking to and your background and level of understanding, and that will help us to tailor the presentation as we proceed. So please answer those questions as honestly as you can. The survey and the rest of the surveys we will run today are anonymous, so we're really just polling the audience to get a feel for who we are talking to. I'll give you a few more moments to consider those questions and to submit your answers, and then we will take a look. I'll show you the responses that we've had to the questions before we then proceed with today's agenda. So I will bring that survey to a close now, and let's take a look at how you have responded. So the first question then, what is it that makes testing audio playback devices a particular challenge? The majority of you have correctly identified that the challenge that we face here is that we have no dedicated audio input port for these types of device. Now I'll explain exactly what we mean by that. I have a couple of slides to illustrate this, but I just wanted to ask you that just to get a bit of background to see how well you understand this topic before we start. So it's good that the majority of you appreciate that. We will then go through explaining how we go about addressing this particular challenge, this lack of a dedicated audio input port. And just looking at the second question, we have a good range of participants here today, from design and manufacturing engineers to those who are attending because they have an interest from a research or academic point of view, and we have other people here perhaps for other reasons and because audio is a hobby for them rather than a profession. So hopefully there's something here today for everyone, and as I say, if you do have any questions as we go through, please do send them in, and we will do our best to answer all those questions by the end of today's session. So then, let's just quickly go over today's agenda. First of all, we're going to come back to this question of what it is that's challenging about playback-only devices, why this lack of a dedicated input port gives us one or two challenges to overcome. That will lead on to a discussion about test files, and I'll make that connection more clear as we go through. We will then talk about some specific types of measurements that you might want to perform on your tablet or playback audio device, and we'll look at single tones, sweeps and multi-tones in particular, and we'll ask questions about how many of these types of measurements can actually be accomplished if you have no dedicated input port on your audio device. We'll then spend a bit of time talking about what you might want to do if your playback device incorporates some form of digital audio output or outputs. And we will then consider a particular category of playback devices that I will explain in more detail when we get there, but we're going to look at PC audio interfaces on tablets and laptops and PCs, etc. Then finally, we'll put everything together that we've discussed in the preceding sections and show you a real-life worked example of a playback audio device test, specifically a media player, a test that was implemented on a production line, so automated. Okay, so let's go to the first part of today's presentation then and consider the challenge. What is it that's difficult about testing playback-only devices? Well, before we get to that question specifically, let's just look at how we go about measuring what we might call a conventional audio device. And for the sake of argument, I have taken a power amplifier as my conventional audio device. So how would we go about measuring the performance of something like a power amplifier? Well, we would need some form of audio test and measurement system, and the one that I'm going to be using extensively today during my demonstrations is the Prism Sound D-Scope Series 3 test and measurement instrument. And we would connect this to our device under test. So we would take our generator output, connect it to the input terminal, the line level input of our audio power amplifier, and we would then take the output of the amplifier and connect it to our analyzer inputs, usually via a resistive load. This is a simplified schematic here. So this is a loop-based measurement. It's a closed loop where we're involving both the generator and the analyzer of the audio test system. And this is how we would go about measuring, as I say, a conventional audio device. So how is this different from a playback device? Well, the majority of you from our survey already are happy with this next point, but I want to make it completely crystal clear so we're all up to speed. Let's look at some playback devices. So here we have a media player, I have a tablet, a smartphone, a laptop, a disc player, portable gaming device, internet radio, docking station, and here an AV server system. All these devices share one thing in common, and that is that none of them have a dedicated audio input terminal. So we can't easily pass audio from one end of the system through the system out the other end. In other words, our closed loop tests are not possible. And we like to use closed loop tests if at all possible because it makes testing simple. That the test system is aware of what its generator and its analyzer is doing, and it makes it easier to synchronize more complex tests like sweeps, for example. However, this isn't possible in the most part with these types of devices, so we're going to talk about how we overcome that challenge. And the first thing that we need to be aware of is that because these devices don't have an input, we need some kind of test file that can be loaded or saved or streamed through our playback device in order that we can generate a test tone and analyze it. So let's consider first of all the output direction, the playback direction of our device under test. And here I have once again the system that I'm going to be using extensively today, the D-Scope 3 measurement system, which comprises a software interface and a hardware instrument. And this is the device that I want to measure. This is my tablet device, and I want to analyze the behavior of its analog output via its headphone port. How do I do that? Well, I need to load some test files onto that device, play them out, and then analyze the output of that device. What about the input direction? Well, there are many devices, tablets, laptops, smartphones, etc., which may have inputs, and in particular systems that are designed to handle voice, so microphone inputs are quite common on these types of devices. How would we go about testing a mic input? Well, ordinarily you could use a loop-through test, but perhaps not for this type of device. On my tablet, what I would do would be to connect a signal from the test system's generator to the mic input and then record an audio file which can then be analysed offline. So that's the basic idea. Let's now start to develop this into some practical real-world examples. And let's first of all dwell on the question of the test file itself and how we would go about creating a suitable test file for loading onto our playback device, which will then allow us to analyze it. So we've already seen that there is a need to create test files. Typically we're dealing with WAV files, so linear PCM format. In other words, uncompressed PCM digital audio that will give us the highest quality signal possible. And that's important because what we don't really want to do when we're measuring these devices is to analyze the performance of the codec. That may be something we want to do independently, but from the point of view of analysing things like the power amplifiers, the signal processors inside our playback device, we want to play a high quality linear PCM file if possible. So how do we create this file then? Well, one option is to use some audio editing software, and I've just got a very quick example here of this is actually a freeware audio editing system called Audacity that allows me to do things like generate a test tone here. I can choose my frequency, let's choose 500 Hertz and a length of 250 milliseconds. So I can generate a tone. There it is. I can see the sinusoidal waveform I've just created there, and we can then export that as a WAV file, which can then be loaded onto our playback device, played out, and we can then test that device. So that's one option, using audio editing software. Another option would be to use a test disc, and there are quite a number of test discs available on the market, and they contain lots of useful test tones that could potentially be used for this purpose, either for testing a disc player directly, or you could lift the files off the disc and save them onto the device that you're testing. The final option that I want to mention here is that Prism Sound does have a freely available tool for creating WAV files, and I'll show you a little bit more about that particular application a bit later on, but it's a very useful tool that allows you to generate your own test files that meet your own specific requirements very easily and very quickly. Okay, so we talked about the need for test files to analyze these types of devices. Now let's look at a few examples of some of the tests that you might want to make on this type of device. So we'll consider single tones, sweeps, and multi-tones in this section. Firstly then, let's look at a single tone test. And as I've already explained, firstly we need to create a WAV file. And I've already shown you that that's actually very straightforward in audio editing software. One thing you do need to be concerned with is whether or not your editing software is accurately creating the amplitudes, the frequencies, and in particular the dither when it truncates the signal to a fixed word length. That's something that is taken care of in professional audio systems like the Prism Sound Sadie software, but you do need to be careful because it's a little bit difficult to verify whether your editing software is doing exactly what it claims to be doing. Test discs, these usually come from fairly reputable sources, and you should be fairly confident that the test tones on your test disc, which will almost certainly include some sinusoids, they should have been generated with some care, and you can be reasonably confident that the test tones there are fit for purpose. Prism Sound Test Tools, well, we are a test and measurement manufacturer. We have taken great care to ensure that this WAV file generator that we've created does create tones with accurate frequencies, amplitudes, and dither to the correct word length. So this is another option available to you for a single tone test. So let's now then look at a demonstration, put this theory into practice. And what I'm going to do is, as we saw in the previous slides, I'm going to take my tablet. I have connected the analog outputs of this tablet to the analog inputs of my measurement system, and I'm going to play a sine wave that I have previously encoded as a WAV file and saved to my tablet device. So I will now switch to my D-Scope Series 3 measurement system. This is the software where we can see the measurement results on our screens, and at the moment there's not much happening. I have no signal present, but if I now go to my tablet and turn on or play one of my test files, I'll start with my 1 kHz sine wave. I'll just turn the volume up on the measurement system. We have a monitor that allows you to hear what you're measuring. I will now play the tone. So there you can see we have a number of results on the screen, which I will talk you through in just a second. And I've actually saved a few WAV files on my tablet, so I can, for example, switch to a 2 kHz tone. I've also got a higher frequency one encoded at 10 kHz. And I've got a low frequency one down here at 100 Hz. So there's quite a lot that we can do with a basic sinusoidal measurement. And if I just switch back to the 1 kHz tone, I shall explain very briefly what we have on screen. I'm not going to dwell too much on the analysis side of things today. I'm going to focus more of my attention to the methodology of actually achieving a measurement result using a playback device. So firstly, here we have our trace window, and you can see that we have a green curve here showing you the live time domain trace of this, in this case, 1 kHz sine wave. In red, we have an FFT trace showing you the spectrum of the signal that my tablet is creating. And in blue, we have a residual noise and distortion trace. So this is the output of this filter here. We're removing the fundamental, and we're just going to listen and just going to look at the residual noise and distortion. So in addition to being able to monitor the tone, I can switch to monitoring the noise and distortion. So that's quite a useful audible check in parallel with all of these numerical measurements that we're making. So I have a screen full of numerical readings here, and this is just something that I configured. It's completely arbitrary. I've just set this particular measurement up to show you an example of some of the analysis results that you might want to see. And if the result you want is not on the screen, we have up to 40 of these unique smart FFT detectors that allow you to hone in on exactly the parameters that you want to measure on your device under test. So for the purpose of my illustration, I'm measuring here in the top left THD plus N, so total harmonic distortion plus noise. I have the residual noise measurement here, the total harmonic distortion in isolation, so now I've been able to isolate the noise and the total harmonic distortion components that were included in this THD plus M result. I've got a second harmonic distortion, third harmonic distortion, fourth harmonic, fifth and sixth. I could have gone on, but I ran out of screen space. I've got a mains hum measurement here. I've got some amplitude readings in different units. So I've got milliwatts here, I've got volts here, and I've got the frequency and interchannel phase readings. So these are all types of results that you might want to see when conducting your initial sinusoidal analysis on your tablet or other playback audio device. As I say, I don't want to dwell too much on the analysis and what all this means. We've dealt with that in other webinars. I want to focus more on the method for testing this particular type of device. So I shall move on for now and consider the input direction of this tablet. So how would we analyze that? Well, as I explained earlier, we take our playback device here and connect the generator from, in this case, the Dscope 3 hardware, and we record a WAV file on this particular device. I have done that recording offline. I'm just going to jump to a new test setup here that's all ready to do the analysis for me. And what I can do here, in order to measure the input direction of this device, which has no loop-through terminals, I can load that recorded WAV file into the analyzer. So if I hit the import button here, I can now load this file, tablet mic input.wav. This is the file that I previously recorded on my tablet, and this will allow me to characterize its input signal path. So I've loaded that file, and now we see on our trace window we have this green time domain representation. This is the, I'll just click on this particular waveform. This is effectively the WAV file that I loaded into the analysis buffer, along with all of its time domain sample values. We've converted that into a corresponding spectrum, so the red trace here, this is the FFT showing you the spectral makeup of that particular signal. And once again, we've broken that down into these numerical readings, which show you in very fine detail the performance of this device in terms of its distortion, its noise, its mains hum, etc. So that gives you a quick idea of how you would go about measuring your tablet or your other playback device inputs and outputs for a sinusoidal test signal. So let's move on to sweeps then. And what I firstly want to do is to ask the question, is it possible to perform a sweep on a tablet or another playback device? So let me put that question to you. And once again, I will run a survey. And for those of you using a PC, you will have a question on your screen right now saying, is it possible to conduct a sweep measurement on a playback only device? So please consider that question and let me know what you think the answer is. Once again, it is an anonymous survey. We just want to get an understanding of your level of understanding of this topic. So I will give you a couple more seconds to answer that question, and then we will take a look at your responses, which we will do now. So the survey has now stopped, and excellent. That's a very good response. We have almost a unanimous response where you think that swept measurements are possible with a playback-only device. Well, yes, I can confirm that you are quite right. You are able to perform a swept measurement on a playback-only audio device. How do we do it? Well, we've already explained one half of the answer, that you need a file. Let's explore the other half of the answer. Now, we need to be careful in order to be able to correctly synchronize the test system such that it is able to make our sweep measurement for us. And in the D-scope system that we're looking at today, the way we do that is to use what we call a sense sweep. So in other words, we are able to sense the incoming amplitude or frequency depending on the variable of our sweep in order to be able to complete a sequence of individual tests at either discrete amplitudes or discrete frequencies, and to join them up in a two-dimensional graph to give us an understanding of how our device performs with respect to either amplitude or frequency. Again, that's normally straightforward in the conventional audio measurement sense, where the generator is applied to one of the input terminals of the device under test, but in a playback device, as we saw, this is not possible. So let's go back then and consider the question once again of how we create a suitable file for performing a swept measurement of our playback device. Well, you could try and tackle this using your audio editing software. It would be possible to generate a series of discrete sinusoidal waveforms, join them all up together, export that as a single wave file and load that onto your device that you're testing. That's fine, but it is a little bit time consuming. That's probably the biggest problem with that particular approach, and it will take a little bit of experimentation to get the right duration for each tone frequency or amplitude. And yes, it's possible, but it's probably not the most elegant method for tackling the problem. Test discs, well, they quite commonly feature sweeps. The main concern here really is that the sweeps on your test disc may not have been optimized with your priorities in mind. So for example, the sweep may not have minimized the duration at each particular tone amplitude or frequency in order to keep the test sequence to a minimum. For example, if you're working on a production line, you may be concerned with performing your tests in as short a space of time as possible. It may be that the test disc doesn't have a sweep with fine enough resolution for the measurement that you're trying to make. The point here is that you can use a test disc, but it may not be perfectly optimized for your needs. So the third option is probably the one that I would recommend for most situations when performing a sweep measurement on a playback audio device, and that is to use the free Prism Sound tools that I'm now just about to give you a quick introduction to. So we have this wave file generating application that I'll talk you through briefly, just to give you an understanding of what it does and how. So first of all, we can create either a static tone or a sweep. So if you want a static tone at 1 kHz, you just simply dial in 1 kHz as both your start and your stop frequencies. And you have the same option for amplitude. We can either start and stop at the same amplitude, or we can go over a range of amplitudes. It's entirely up to you. If you're sweeping over a range of frequencies, which is what I want to do for my next demo, let's say from 20 kHz to 20 Hz, the normally accepted audible range, We can then dial in a number of sweep steps, depending on the resolution that you want for your measurement. We can choose whether we want a linear or logarithmic interval of frequency steps, and we can choose the duration of each sweep step. So this allows us to minimize the time that we spend measuring by ensuring that we have just enough time to make the measurement, but not too much time spent at each sweep step unnecessarily. Just jumping down to the bottom here, we have the option to encode our WAV file at whatever sample rate we want to work at, and we can choose our word length and whether or not the file is mono or stereo, or indeed potentially a multi-channel WAV file. So having selected our criteria, in this case I wanted to make a 20-point sweep from 20 kHz to 20 Hz, I then simply hit the Generate File button, and this little application takes care of the rest. So it has now created a WAV file, and offline I saved that WAV file onto my tablet with a view to performing the next live demo, which I'll just talk you through now. So once again, our familiar looking by now D-Scope Series 3 measurement system, my familiar looking tablet, and I am playing back the swept file that I've just talked you through that I generated using the application I have just shown you. So once again, let's jump into the D-Scope Series 3 system, and I'm going to take a shortcut to the sweep measurement file by hitting this button here. Okay, so I've got this page of the configuration open, and in particular I want to show you the sweep setup panel here. This is where I've defined the results, first of all, that I want to measure, and I want to measure frequency response and distortion response, so total harmonic distortion plus noise as a function of frequency and amplitude as a function of frequency. So we have a number of options available to us, and I've chosen channel B and channel A RMS amplitude at the top here, and channel B and channel A THD plus N as my third and fourth results. So that tells the measurement system what it is I want to measure, and now I have to make sure that I tell the test system how I'm going to measure it. And the conventional method for running a sweep would be to vary either the generator frequency or the generator amplitude. But we've already seen that that's not appropriate for playback devices such as tablets and the other types of systems that we looked at earlier. In this case, we need to use the sense frequency or sense amplitude options in the D-Scope system. And it's a frequency response I want to measure, so I'm going to use the sense frequency option. And I've told the measurement system the frequency at which I consider the sweep to be complete, and the threshold above which I consider the test to have commenced. So in other words, when the signal goes above minus 60 dBu, the test will start. One final thing, I've just put a memo on my desktop here. These are just memos that you can write to yourself to remind you to do certain things. And the first thing I want to do is to set up my, my 0 dBr reference level. So that allows me to plot my frequency response relative to the level at 1 kHz. So firstly then, let's play my 1 kHz tone on my tablet, which I'm doing now. And by hitting these reference buttons here, I can use the current signal amplitude, in this case just over 28 milliwatts, as my reference level at 1 kHz. So now when I run my sweep, everything will be plotted relative to that reference point. Okay, so I'm ready to run the sweep. When I hit the button here, this arms the sweep, which is currently now sensing, it tells me, and it's waiting for the signal to exceed that minus 60 dBu threshold that I dialed in the previous screen. So I will now play my sweep WAV file on my tablet, and we're underway. So now you can see the measurements executing on screen, and I've slowed this sweep down to the point where we can actually see live FFT updates and live trace updates as the sweep is executing, just to give you an idea of what's actually happening here. So we're playing through this WAV file, and the frequencies are progressively stepping downwards from an initial value of 20 kHz to the final value of 20 Hz. So there is my sweep result, and I will turn off the traces that I'm not interested in any longer. And let's firstly look at the yellow and the pink curves. So this is channel A on the top, channel B on the bottom. We may wish to overlay them, and that is our frequency response. and it's broadly flat, as we'd expect from this kind of device, over the 20 Hz to 20 kHz range. And secondly then, the other result that I asked for was THD plus N as a function of frequency, and that result is now on screen for you to see as well. So again, I'm not going to dwell too much on the analysis and what the results tell us. I just wanted to show you the theory and practice of how to go about performing this type of measurement. So having done that, I'm now going to go back to my slideshow and talk about the last part of this section of the presentation, and that is multitone testing. Again, multitone is a complicated topic all of its own, and it's something we covered in a past webinar. I don't intend to dwell on the background of multitone too much today, other than to say that it is a very fast and powerful measurement method for enabling very quick go, no-go decisions to be made, for example, on a production line. And the D-Scope 3 system that we're looking at in detail today supports generation and analysis of arbitrary multitones. So whatever multitone you want to create, the D-Scope 3 system is capable of creating it and of performing the subsequent analysis. This is what the multitone generation and analysis tools look like in D-Scope. We'll see this in a bit more detail in a second. In particular, the thing that I want to bring to your attention is that when you're dealing with a playback device, such as a tablet or a smartphone or all the other types of devices we've been discussing, we have an option here to generate a WAV file containing this multitone. So if we go back to our question of how to create a WAV file for this purpose, well, it's going to be very difficult to use audio editing software to define accurately an appropriate multitone. When you're setting up a multitone, you need to be very careful about ensuring very, very specific signal frequencies. So your audio editing software probably isn't the best solution for creating a multitone. Again, test discs probably don't have exactly the multitone that you need for your application. They may do, but they may not be the best way of creating your test files in this case. What I would recommend, if you're using something like the D-Scope 3 system to perform your multitone measurements, you should use this system for your multitone creation and export the WAV file. It's by far the simplest and probably the most flexible and appropriate way of creating a multitone file for testing your playback device. So let's do a quick demo then to put this theory into practice. Once again, I've got my tablet. I have loaded a multitone file that I created using the D-Scope 3 system onto my tablet, and I'm going to play out that multitone file and perform a measurement. So I'll launch my multitone test file here, and I'll just briefly talk you through the multitone generation and analysis tools. There are quite a few more degrees of freedom than there would be just creating a sinusoid or perhaps even a sweep. There are many more variables here in a multitone. For a playback device, one of the most important things that we need to be aware of is that we need to set up the analysis as asynchronous. The clocks in the playback device are not synchronized with the test system, so we use the asynchronous analysis mode here. I can choose how many tones I want. I can choose my highest and lowest frequency tones. I've selected this option here to automatically generate the highest possible amplitude and to minimize the crest factor in order to give me the best possible analysis signal to noise ratio. And as we saw, importantly, I have selected the generate WAV file option, which will give me a file that I can then load onto my tablet, my smartphone, my laptop, my AV server, and play that file out for the purposes of analysis. Looking briefly at the analysis side itself then, we have a number of options available to us, both numerical readings and also graphical results that we can obtain from a multitone analysis. And as I say, I'm not going to dwell too much on the detail, but we will make a measurement and look at the result, which I will do now. So the system is up and running. You'll notice there's nothing happening on the screen at the moment. You normally use what we call a single shot measurement mode for a multitone because you're just wanting to do a quick go, no-go measurement, and that is normally just conducted once. So I'm going to play the multitone and let you hear what it sounds like first of all. So that's the file playing out of my tablet and being received and amplified so you can hear it by the measurement system. That is playing continuously. Now I'm going to make a measurement. So 3, 2, 1, go. And the measurement has now completed. So you can see this on your screen. And the red trace here, this is the FFT of the time domain signal. And this shows you quite clearly the discrete tones in this particular multitone. And from this FFT information we can derive all of the other traces. So first of all we have this yellow trace, that's our frequency response, once again pretty close to a flat line as we'd expect. But we also now have this distortion and noise response in blue and a crosstalk response in green. And the crosstalk has been derived by carefully selecting the tone frequencies such that the channel A tones are offset from the channel B tones, and this allows us to look at the gaps in between the tones to analyse the crosstalk performance as a function of frequency. Now, in addition to these graphs, we're also producing a series of numerical readings which are integrating parameters like total distortion and noise and crosstalk across all frequencies. So this is a summation of all the noise and distortion and all of the crosstalk components respectively. We've got other readings here, for example the low frequency roll-off, high frequency roll-off. We have the interchannel balance here, so a measure of how well balanced the two channels of the stereo system are, and also a wideband amplitude reading here. And if I just crudely emulate a fault in my tablet device by turning the volume down, I can rerun this test. So there's my file still playing out. I can rerun the test at a lower signal volume on my tablet, and now we see that the device has failed test. That was a very quick test that took a couple of seconds, and instantly we've got all of this information and critically the information telling us that this particular device failed test. Okay, so we've now dealt with a bit of the background theory about testing these particular types of devices, playback devices that don't have a dedicated audio input terminal. We've seen that we need to create test disks or test files in order to analyze these devices, and we've looked at some measurements of the audio data for single tones, sweeps and multitones. I've been looking at analog domain measurements up to now. I want to just spend a bit of time talking about digital audio measurements. There are quite a few of our playback audio devices that will feature some form of digital audio outputs to connect to a digital receiver downstream. What I want to do now is ask you what you think is the most efficient, most straightforward, simplest method for testing a digital audio system where the system is nominally supposed to be able to handle digital audio without affecting it. In other words, in crude terms, bits in equals bits out. If that's your digital audio system, how do you think we should go about testing it? And once again, I've got a survey that will be on the screens of those of you who are using a PC, asking you to consider that question and tell me what you think the answer is. So I've got a few different options for you: THD plus N, THD, multitone, frequency response, or transparency stroke bit test. Please let me know what you think is the best, most efficient method, the simplest way of testing a digital audio device who, as I say, nominally is supposed to behave in such a way that the digital audio is played perfectly, bits in equals bits out. So let me know your thoughts. I will publish those results in just a second. So let's take a look at how you responded. And again, the majority of you are you're doing very well today actually. You have correctly identified that the simplest method for this type of test that I've just talked about is using a transparency test or a bit test. And in simple terms, we take a known sequence, pass it through the system we're analysing, and check that what comes out is what we put in. Again, that's relatively simple to do in a loop-through or closed-loop measurement scenario, but it takes a little bit more care to implement with a playback-only device. So let's consider that then before we actually show you the practical demonstration. So as I say, it's quite straightforward to test a digital audio device that's supposed to handle digital audio transparently. We don't need to concern ourselves with making frequency response measurements, noise measurements, distortion measurements, crosstalk analysis. We can do effectively all of that in a very simple test by just ensuring that bits in equals bits out. In other words, the digital audio has not been affected in a negative way by the device that we're testing. And we have a particular type of stimulus or test signal for doing that using the Prism Sound test system. We call it the channel check sequence. And this particular sequence is very attractive for this playback only scenario because it can operate with arbitrary latency between the device that generated the test sequence and the device that is analysing the test sequence. In other words, perfectly well suited to file-based playback from our tablet or our smartphone or our media server or whatever else we may be concerned with analysing. So if it's got a digital output and we expect it to process digital audio perfectly, this is a good way of testing it. So if you are a Dscope user, and a number of you on the session today are, then this is how you go about setting up a transparency test. You go to the digital outputs and select the channel check sequence rather than the generator as your source for your digital audio data. At the analyzer side, you simply dial in the channel check for the number of bits that you are attempting to test. And in my case, I'm dealing with, well, I'll tell you what I'm dealing with in a second, but it's a 16-bit device, so I'm using the 16-bit channel check sequence. Now, of course, we can't play this signal through our device in a closed loop, as we've already discussed, so I previously made a recording of the digital output from the Dscope using our bit transparent, bit perfect SADI digital audio recording system. So I know that I've got a perfect rendition of Dscope's channel check sequence. Do we have any alternatives to doing it that way? Well, it's extraordinarily unlikely that your audio editing software will support this. I know of no audio editing software that is able to generate the Prism Sound channel check sequence. Test discs, there may be test discs out there that could be produced. It's perfectly possible for somebody to make a recording of our channel check sequence and record that onto a test disc. But it will be probably difficult to find. So my best recommendation for performing this test would be to use a bit perfect recording from the Dscope digital outputs using the Dscope Series 3 test system. And that is exactly what I did. So once again, I'll talk you through the demonstration that I'm going to show you. Now for this test, I'm using an off-the-shelf consumer product. It is the i20 dock from Pure, and I know that this device is bit transparent. I have tested it, verified that it works bit perfectly, and so I'm going to use it to illustrate this concept of doing a digital audio test. Now this i20 dock has in fact two digital outputs. It has Toslink and that's Toslink optical, and it has SPDIF electrical. I could test either of those two outputs using the Dscope. For the sake of argument, I've taken the electrical output for today's demonstration. And I have a smartphone connected to my i20 dock, and my smartphone has been previously loaded with my bit perfect recording of the channel check sequence that was originally generated by the Dscope 3 system. So this is the measurement setup that I have on my desk, and I'm just going to very quickly show you a demonstration of testing whether or not my playback device is behaving bit transparently. So once again, let's go into the Dscope system, and I'll take a shortcut to my digital audio transparency test. Okay, so right now nothing's happening. We're looking at a screen showing us no live data. We've got a signal amplitude here of effectively digital 0 minus infinity dB, and we've got a red light in the channel check sequence. That is because currently my smartphone is not playing anything, but as soon as I press play on my i20 remote control, my smartphone will play out my channel check sequence, and I can test whether or not the phone and the codec used to encode the file on the phone, this is a lossless compression codec, I can verify whether that's all behaving as it should do. So I will now press play, and the screen comes to life. We can actually listen to the signal if we want to. So that's the monitor outputs from the Dscope Series 3 test system, and we're listening to a pseudo-random sequence which statistically is very close to white noise, and it sounds like white noise. So this is a very good test for looking into potential bit errors in your playback audio device. And right now everything's perfectly fine. I've got a green light, but I might want to run this test over an extended period of time, and I might want to walk away and come back later and ensure that this light has always been green. Now, of course, I can't just keep looking at it for indefinite duration, so we have some rather more powerful tools in the Dscope 3 system that do that monitoring for us. And this is what we call our event manager. It's an extremely powerful set of tools that allow us to monitor all kinds of potential intermittent faults in signal amplitudes, in digital metadata tests, and in this case in our channel check sequence. So I've turned on these two checkboxes here, and I am testing for the condition that my transparency test runs without flaws. So I'm just going to restart this file, and I'm going to reset my log file, as I have done now. And we'll see that the test is running quite happily. Everything is behaving exactly as I would expect for this device. Bit perfect, no problem at all. I'm going to emulate a fault with this device by turning the volume down. And on this device we have a digital volume control. So if we turn the level down, we're affecting the gain, we're affecting the digital audio data, and therefore we would expect a failure in the channel check sequence. So turn the volume down, and there we have it. We see an error logged on the screen. If I reset the volume control, we get another message saying that the error condition has been reset. Pause the file, and we get no data, and we get an error in the log file. So this is the important information. This is the error log that doesn't run out of paper, that will sit there in the background happily testing for all kinds of different fault conditions over indefinite periods of time that allow you to test your playback device, ensuring that it is bit transparent over extended periods of time, saving you from having to sit there in front of the screen monitoring the status on an ongoing basis. There are other things that you might want to do in terms of analysing your playback audio device, and it's not necessarily just the digital data that we're interested in. There are other things on a digital output that we might be concerned with, and for example we might be concerned with measuring the embedded metadata. This is what we know as the channel status data, and this just tells the receiving equipment about the embedded audio data and therefore how it should treat it. We can look at this in the simplified textual form, or we can look at it in the advanced form here that gives us bit by bit, byte by byte, all of the embedded channel status metadata information, and allows us to do some clever things like, for example, highlight any inconsistencies, or perhaps highlight any differences from one channel to the other. And in this case, this is a stereo signal, so if I select this highlight differences from other channel, we see a red warning light here telling us that the channel A and channel B metadata is different, but we would expect that for this particular device because it is a stereo stream, and therefore the channel A and channel B metadata identifies the two different streams, and so the metadata is different from channel A to channel B. In addition to the metadata and the audio data, we may be interested in the electrical carrier itself, and here we have a measurement showing us the digital audio frame rate, in this case 44.1 kilohertz, about 10 ppm away from the acknowledged standard frame rate, and we also have a measurement here showing us the amplitude of the electrical carrier, in this case just over 500 millivolts. We also have a display here known as the carrier display or I-pattern display, showing us the electrical signal that is carrying our digital audio data and our audio metadata. And again, I'm not going to dwell too much on the details of what this all means. I just want to give you a quick snapshot of how to go about measuring your playback devices. We've covered a lot of this theory in other webinars that I'll refer you to at the end of today's presentation. Okay, so that concludes my brief discussion of testing our playback device's digital outputs. I'm now going to look at a particular category of, or particular class of playback audio devices, and that is those that perhaps they might be PCs, they might be tablets, they are computers running Windows that have Windows audio devices attached to them, that we might consider to be a playback only device, but I will show you how we can, with the Dscope Series 3 system, go back to testing these types of devices in a closed loop. So how do we do that then? Well, we've already seen the Dscope Series 3 system, and we've seen that it has hardware inputs and outputs for testing digital and analog audio inputs and outputs, but we have a third domain aside from the analog and digital domains that we're able to analyse using the Dscope system, and that is what we call our sound card domain, our sound card outputs and inputs. So if our playback device is a laptop, for example, it will have an onboard sound card with a headphone output and more than likely a microphone input. Now we can address that sound card directly. We can route digital audio signals from the Dscope software to the sound card's outputs, which can then be connected to the measurement system's inputs, and we have now got a closed loop measurement setup as we talked about earlier on in the presentation. And that also goes for the inputs direction, so we can take our measurement system output, connect it to our laptop sound card input, and that can be analysed directly from the Dscope software by routing these digital audio signals through the Windows driver interface to the Dscope 3 software. So laptops and tablets running Windows operating systems might be considered as playback only devices in the context of what we've discussed, but we can route signals to and from them directly in this fashion to give us a closed loop measurement setup. And let me just talk you through an illustration of this, hopefully to put this into better context. So once again, I've got my Dscope 3 system running on the laptop that I'm presenting to you from, and my laptop of course has its own sound card outputs. So what I will do is connect my laptop's headphone outputs to the measurement system, and that will enable me to characterize the performance of my laptop sound card. So let's jump to that test, and I will further explain the sound card I/O functionality. So in the Dscope Series 3 software here, we have access to things like the digital outputs, the analog inputs, and so on, but we also have sound card outputs and sound card inputs. And as I say, that allows us to route digital audio signals directly to our sound card on our tablet, on our laptop, etc. So on the sound card outputs panel that I have open here, I can choose any of the audio devices that are connected to my laptop, and I've got an external Firewire box connected, I've got an onboard Bluetooth chipset on this particular laptop, and I have my onboard sound card with microphone input and headphone output. So this here is my headphone output. If I select this as an output from the Dscope software, you can now hear and see that I'm generating a test tone at the output of my laptop sound card, and I can now choose whatever amplitude, whatever frequency I like. So I have closed loop control once again of my laptop sound card, and that allows me to perform sweep measurements, sinusoidal measurements, multitone measurements, all of the types of tests that we've talked about without needing to use any WAV files. And just to illustrate that then, just to put this into context finally, I'm going to run a swept measurement, and in this test I'm going to measure THD plus N, so total harmonic distortion plus noise, as a function of the generator amplitude. So I'm going to plot distortion versus amplitude. And I'm going to vary my generator amplitude from minus 30 dB relative to full scale up to 0 dB, so maximum digital domain signal amplitude. And rather than plotting this against the generator amplitude, what I'd like to do is to plot it against the measured output power. So I've actually got my laptop headphone output connected to a 32 ohm resistive load, and I'm measuring the voltage across that load to measure the output power. Once again, I've slowed the sweep down so that we can actually see it executing live. Let's run the sweep. And remember, no files involved here. The test system is generating the tones and analysing the information that's coming from my laptop headphone output. So the sweep is executing. We're ramping up in signal amplitude, which you can see on the screen there, and we've then just run into clipping as we generated a full-scale 0 dBFS signal at the end of the sweep there. So there it is. There is our sweep result. The sweep actually, let's just turn off the other traces. The THD plus N versus output power graph is the one that you now see on your screen. The yellow trace for channel A and the pink trace for channel B. So hopefully that now explains how certain types of playback devices, for example tablets and PCs, if they're running Windows as their operating system, we can greatly simplify the process of testing these types of device by using this closed loop measurement functionality in the Dscope 3 software, and preventing us from needing to encode and to play back wave files as we saw in the previous examples. Okay, so let's put all of this together. And I'm going to go back to a playback audio device that isn't a sound card. It's a media player, and I'm going to show you a real-life implementation of a production test that was developed for a client who was manufacturing very high volumes of media players. And for those of you that were paying attention earlier, if I talk about high-volume manufacturing applications, the first thing that should come into your head is multitone. That's probably one of the best methods for performing a comprehensive test in a very short space of time, which is ideal for production line implementation. So I'll just talk you through the measurement setup once again. I'm using our Dscope Series 3. I have a media player, and this media player has a multitone already saved as a file on that device. So I created the file offline using the Prism Sound multitone tools, and I've saved that file on the media player. So let me just give you a quick live illustration then. And as I say, this is a turnkey solution that we developed for a client, and includes all the automation and automatic signal detection that they needed for their particular application. So you will have seen in the background there that when I launched that application, an Excel spreadsheet opened in the background, and this particular client wanted to work with spreadsheets for storing the measurement results and also for handling the test limits for their QC analysis purposes. They didn't want their production operatives to need to be trained in audio test and measurement. They just wanted them to be able to use a spreadsheet to enter the test limits, and for the spreadsheet to do all the handling of the data. So the data exchange with Excel has been automated, and also the signal detection has been automated. So this little panel that has popped up here when the application launched, this tells you the status. It says it's ready. It's waiting for a test file. So as soon as I press play on my MP3 player and the test file is detected by the Dscope measurement system, the measurements will commence automatically. So without further ado, let me press play on my media player, which I'm doing now. And you will have heard in the background that the test file has played out. You heard the multitone, and we can now see the result. The result was a pass, and it took just under 1.5 seconds to determine that this particular device was working as the manufacturer intended. Now, in a production line scenario, you would more than likely have some way of automating entering the barcode information from the device that you've manufactured, probably a USB barcode scanner. But for the purpose of my bench demonstration, I've got a manual version here that allows me to manually enter a serial number. So I'll call this Simon Test 1 for the sake of arguments. And if I go to my spreadsheet, we will now see that the first line of the spreadsheet contains that serial number, Simon Test 1, and all of the measurement data, so frequency response, crosstalk, total distortion plus noise, from that particular pass. And what I'll do finally is go back to my media player, and I'm going to just dial in some bass boost in the EQ settings, and that will emulate a fault in the frequency response, which should be nominally flat, as we can see from this test. So if I dial in some bass boost, I'm now going to go back and play the test file once again, which I will do in just a second. You can see that now the test has failed, and the reason for the test failing is that the frequency response has breached the limits at low frequency, as we'd expect, because I have dialed in some bass boost. So I hit OK. There's a little summary screen here telling me exactly what has failed, and I now have the opportunity to put the serial number in, Simon Test 2, and going back to my spreadsheet, we can see here that there it is, Simon Test 2, it's a fail, and in particular the 40 Hz and 200 Hz amplitude has breached its limit as a consequence of that bass boost. So that hopefully gives you a better understanding of the kind of thing that you might want to do in the real world as a manufacturer if you're producing playback only devices such as the media player that I have just illustrated in this particular demonstration here. So let's close this down for now and go back to our presentation to make our conclusions. So let's just recap what we have covered today then. First of all, we saw that there are many audio devices that do not have a dedicated audio input port, and that presents us with a particular challenge when it comes to analysing the performance of these devices. We can't use closed loop testing, we cannot connect our signal generator to the input of these devices, and therefore we are condemned to using test files for the purposes of measurement. And I've shown you several demonstrations today of how you can use the Prism Sound D-Scope Series 3 measurement platform in conjunction with a free wave file generation application that can be downloaded from our website in order to cater for the measurements that you're likely to want to undertake on your tablets and your other playback devices, smartphones, media players, media servers, etc. And you can download this wave file generation application if you browse your way or navigate your way to prismsound.com/sweep_generation. And I'll ask my colleague Graham Boswell to post that URL in the NetViewer chat so that you can click your way straight to that part of our website should you wish to download that signal generating tool that we have available. And then finally we have seen that if your playback device is a PC type device, either a tablet or a laptop or even a personal computer running Windows as its operating system, we can address the sound card outputs and sound card inputs of those types of devices to allow us to measure in a closed loop in real time, preventing the need to use test files. So a few further topics for further consideration, and things that we've not really had a chance to discuss in detail today. Multi-tone testing we have touched on. Sound card testing we've seen a brief example there. Power amplifier testing, well, we've not talked about that in much detail. Loudspeaker testing, portable media player loudness. These are all entire webinars in their own right that we have discussed in detail in the past, and these webinars are all available to download free of charge from the Prism Sound website, so prismsound.com/webinars, and this is where you will also find information on upcoming Prism Sound educational webinars as they are posted to our website. And again, I will ask Graham if you could post that URL in the NetViewer chat so that you can click directly through to that page on our site. So thank you all once again very much for attending today. I really genuinely hope that you enjoyed the presentation and found it interesting and useful. And we do hope that you join us again on another Prism Sound educational webinar in the not too distant future. So thanks to Graham, my co-moderator today, and thanks once again to you, the audience. So we will bid you farewell for now and hope to see you next time. Goodbye.